Hello and welcome to your Experiment 2 pre-practical lecture.
Brought to you by the University of Pretoria.
Okay, so let's start off with what is geometric isomers. That's where I want to start the conversation, and essentially what is complexes, because I know the theory course and the experimental course doesn't really run that parallel. So we start off with an Ma4 square planar complex. So what we have here is we have a metal center, and the metal is bonded to 4 A ligands, and those A ligands are on the corners of the square. So if you think of an A4 sheet of paper, and you put the A's on the corners of the paper, and you put the metal center in the center of the paper, and you look at the paper from the side, then 2 of the A's should be pointing towards you, and 2 of the A's should be pointing towards the back of that A4 piece of paper. And that's exactly what we have here. So the thick bonds indicate that A's are coming out of the page or out of the plane, and the dash bonds show that they're going into the plane. Right. So that's a square planar complex. So square planar because it's square and it's planar. And it's a complex because we have a metal and we have ligands. So it's not an organic complex, or organic molecule, so to speak. And of course, these things can have isomers. And you should know what an isomer is from organic chemistry. You get structural and geometric isomers. Structural means different kinds of structures of the same thing, but however, geometric means different geometrical arrangements of the same molecular formula. So Ma4 doesn't have any geometric isomers, and neither does Ma3b. So if we substitute one of the A's for a B ligand, we can rotate this complex the whole way through. So we rotate this way around, this complex this way around in the plane. Then we can rotate that B through all the positions, and we see it's the same complex the whole time. There's no isomers. However, if we were to substitute another B, then we see, okay, that B can either be those two B's can either be separated by 90 degrees and these two A's by 90 degrees, or the B's can be separated by 180 degrees and the A's can be separated by 180 degrees. Right, so that is where the point of a geometric isomer comes in. So we can have the same molecular formula, A2B2, A2B2, but we can have different geometrical arrangements of the same molecule. Right, so the same molecular formula, different geometrical arrangements. Okay, and that leads to a concept that you are aware of, which is cis and trans. So cis meaning same, so 90 degrees on the same side, so those B's are on the same face, if you want, on the same side, so they're always next to one another. And then the trans, they're opposite one another, so opposite 180 degrees. You can see that. And that's just for square planar complexes, which is the easiest complex to start off with. Should be easy to see, and you should be able to draw these things quite easily. And now, what's the big thing that we know about isomers? Well, isomers, of course, have different properties. Now, why do they have different properties? Well, firstly, we have different ligand-ligand repulsions. So there we have AA, we have AB, we have BB. And in this trans isomer, we have AB and just AB and just AB. Right, so you can immediately see this B is pushing off this B is also pushing off this A, and this A is already pushing off this A. But here we just have the same type of repulsion right through. So that, of course, is going to affect the energy of this complex. That's already a difference between the two. We also have different ML bonding patterns. So we have AMB, AMB. Here we have AMA, BMA. So we have different distributions of the electron density. And of course, different distributions in electron density will lead to differences in electronic structure. So a difference in electronic structure leads to different properties, and then that eventually evolves into differences in color, different physical properties, reactivity, and biological activity, just as you know what isomers essentially do. So isomer, different, same molecular formula, same, but different, right? Great. Okay. So now that we have square planar complexes, we've seen it there. We know how to identify cis and trans in square planar complexes. Let's go to octahedral complexes. So we add 2 more bonds. So an octahedral complex has 2 axial bonds that are added. So on top and below the plane, the square planar plane, which I've left in there for you, so you can still see the square planar plane, I've added 2 axial bonds. So the easiest one to start, well, the easiest one is actually MA6, but that's redundant. So let's start with MA5B. Then we can rotate that B to anywhere there. You see there's no isomers for that complex, right? But if we have 2 Bs, again, we can either have them separated by 90 degrees, or we can have them separated by 180 degrees. Great, so we can either have cis and trans complexes again in octahedral complexes as well. And of course, these A's and B's are assigned according to the atom that is bonded to the metals. In other words, and it depends as well on the type of molecule. So let's say, for example, you only had water ligands. So all of these were water ligands. You would assign them all A. If you had 4 water ligands and an oxalato ligand, then you would have exactly 4 A's and 2 B's. Okay, that's how you assign these things. So you need to look at the atom and also what the atom is connected to at the back here, because these 2 A's could, for example, be connected to something else. So let's say this was an oxygen, this was an oxygen. These could all be 6 oxygens, but they could be from different molecules, and that causes these 2 to be different from the rest. Okay, and that then makes them an Ma4B2 type octahedral complex, which causes it to be cis or trans, rather than just seeing, oh, it's just oxygen. And so in other words, it's just the normal, it's just a complex. Okay, this will make a bit more sense later on when we start looking at the complexes. But yeah, for now, you should be able to recognize this and should be able to draw this just, thick bonds, dash bonds, quite easy. Just one note on the octahedral complexes, they have one more type of isomer. And these isomers are called facial or meridional. So if you have a third B, so Ma3B3, then you can have a third B. So on the face, if they're separated by 90 degrees, so sort of the 3D version of cis is facial, and if you have them separated by 180 degrees, so the 3D version of trans, then you have meridional. You might argue square planar would also have a meridional if you have an Ma3B square planar complex, but that's actually just redundant. If that didn't make sense, then we just move on. That's also perfectly fine. Okay, so this was just for interest sake. We don't have, but so octahedral complexes, these are all the type of geometric isomers. Remember, geometric isomers is how they are connected in space, not structurally. So just have that. So we're dealing with geometric isomers in this practical specifically. Okay, so we're dealing with isomerism in chromium complexes. And the 2 types of complexes we'll be looking at is Ml2 and Ml3 complexes of chromium with oxalic acid. And that's abbreviated OXO, so oxalic acid OXO. So we can either have 2 oxo ligands in our chromium complex, and if we have 2 oxo ligands, then we're going to have 2 aqua ligands in the complex as well, in the inner sphere. So how I get to that is, if you have to substitute the number 2 over there, then it's 6 minus 2 times 2 is 2. If I have a 3 over there, then that becomes 0. So if we have a tris oxo complex, then we only have chromium oxo ligands. If we have an Ml2 complex, then we have 2 aqua ligands as well. And we'll start with the Ml2 complexes on the next slide. Right, so for the Ml2 complexes, we can get the cis and the trans. So these are experiments 2.1.2 and 2.1.3. And you can see the cis and the trans quite clearly here in the 3D models that I have here in the aqua ligands. So you can see here's an aqua ligand and there's an aqua ligand. So aqua ligand, just a water ligand. It's bonded through the oxygen moiety in the aqua ligands, and they are separated by 180 degrees from one another. So you can see there is the bonding path, there is 180 degrees, And in the cis one, you can see they're separated by 90 degrees. Right, so cis and trans. This is octahedral complexes. You can see there's 6 bonds to the chromium. All of these ligands are in the inner metal sphere, so it's part of the octahedral. So that's why it's octahedral complex. And of course, you might notice that there should be charges associated with these complexes because all of these oxygens have a minus charge of these oxalato ligands. So that's -4, and the chromium is +3. So there should be a minus charge at each of these. So there's a potassium that crystallizes alongside these complexes. Right, that's why it's called potassium something something. Anyway, okay, to get to the point, so we know they're isomers. That means they have different properties. So what are these different properties? We know that the trans one is nonpolar, big shock. So why is it nonpolar? Because there's no dipole moment because all of these ligands cancel one another. That means it has low solubility in water. Water is a polar solvent. It makes sense because it's nonpolar. And it is it's actually slightly soluble in ethanol, but soluble in ethanol. In contrast, the cis isomer is polar because there's a difference in dipole moment. We have a water molecule here. We have an oxalato oxygen there. There's definitely a dipole moment in that direction, dipole moment in that direction. So it means the molecule has a net dipole moment in some direction. You can draw these for yourself and figure out exactly to where it is. Because it's polar, it means it's highly soluble in water and it's insoluble in ethanol. I'll leave you because it's part of the assignment question to figure out why. So partly is of course part of it's the argument of the polarities, and you need to draw and say why, but also the solubility of the ethanol. Go and read up about what is ethanol classified as in terms of a solvent. Really interesting read. Anyway, just trying to keep this lecture shorter than 3.5 hours. Okay. Now, there are some stills, so now you can clearly see, these bonds are coming out of the plane, going into the plane. These are your axial bonds coming out of the plane, going into the plane. Maybe these can help you draw the complexes. So how do we synthesize these selectively? Because, of course, if you have isomers, it means that the same reagents are going to give you the same products. Because, both of these, same molecular formula, so we can't really control, or I say control, but, nature doesn't really, there's not one of them that are favored energetically or anything like that. Both of them form randomly. It's a roll of the dice. It's the statistical probability on which one is going to form in that specific reaction on a molecular level. So how do we manipulate the conditions to give us the specific isomer? So when we say we're synthesizing the trans one, how do we manipulate the conditions? Well, we just said that this isomer is not soluble in water. So if we place the reagents in water and we synthesize both the cis and the trans, remember the cis form is soluble in water and the trans form is not soluble in water. So when the trans forms, the moment that those reagents react to form the trans version of this isomer, it is going to crash out. It will crystallize from the water and you will form crystals from it. Right, so that's a sneaky way, or a cool, or not a sneaky way, a clever way of forming the trans isomer selectively. So you keep the cis isomer solubated in the water and the trans isomer forms selectively from the water. Similarly, we will do something like that for the cis isomer. So unfortunately, here we can't use the same trick again. Here we need to do something called the heterogeneous reaction. And we will use the fact that it is less soluble in ethanol. So we will have some reaction where both are dissolved, and we will use ethanol to drive out the cis isomer from the solvent via something called titration. Now, titration is just a fancy word for recrystallization. And you've been introduced to recrystallization in your organic course. You've also been introduced to rotovap. So rotovap and all those things are all sort of a group of techniques that we use in this vein. So you use an anti-solvent. So if something is not soluble in this solvent, so in other words, you have it dissolved in this, you have it dissolved in something, and now you take an anti-solvent, anti-solvent, something it's not soluble in, and you put that something it's not soluble in into that solvent, and then you drive it out to crystallize out. Those are the two techniques that we will use. So this one, we make use of its polarity to drive it out. This one, we make use, again, technically of its polarity, but the fact that it's not soluble in ethanol to drive it out via titration, which is recrystallization. Okay, and heat it up, crystallize it at the cooler temperature, make nice crystals. Okay, so that's how we selectively synthesize these two complexes. Okay. Then thereafter, we want to test purity, and essentially, we're going to do a qualitative measurement using a polar solvent. So if we use a polar solvent, what should a qualitative measurement give us? So first, we can use colors because they have different colors. So we can just use our eyes to say, is this crystal pure? So if we expect this crystal, so the one crystal to be orange and the other crystal to be green, and we see a crystal that is green and orange, then we say, okay, it's not pure, right? Okay, cool. So that's the first one. Solubilities, if we expect, so which one do we expect to be solubated in a polar solvent? Maybe the polar complex, yes, all right. So if we use a drop of ammonia on both of them, we expect the one to dissolve purely in the ammonia and the other one not to dissolve, right? So we expect the polar one to dissolve and the non-polar one not to dissolve. And the qualitative measurements, we mean we can't quantify these things, we just qualitatively comment on them. We say the colors are pure, there's no mixture of colors, as well as the solubility, the solubility test, the polar one dissolved and the non-polar one did not dissolve. That's qualitative chemistry. Right. So that's I think that's experiment 2.1.4 is to test this. And this you will do, of course, in the second week once you've crystallized your product. Maybe you're lucky and you crystallize in the first week. If you're not, then you'll do it in the second week. All right, cool. So that's essentially that for the synthesis and the purity and whatever for this part of the prep. The next part, I'll be focusing on now the isomerization of these two. So these two can be isomerized between one another. So we can go from the trans to the cis version using acidic conditions. This is exactly that. So if we want to go, so we place the trans complex in the presence of an acid, we can go to the cis version. And now I asked you a question of what is the rate of this isomerization reaction. And luckily, you are very skilled in UV analysis. You know exactly how to use UV vis to analyze things. And you know how to, because they have different colors, they will absorb at different wavelengths. So in other words, if I tell you that for example, let's use my orange and green analogy again. Remember when I use random examples like orange and green, I just try to use random examples, not necessarily the exact colors that you will always get. So the one is orange, the other one is green. And now let's say the orange one is going to the green one. We want to determine what is the rate that orange is turning to green. We can monitor either, so we have a spectrometer that monitors either orange or green wavelengths, and it sees how quickly there's more green wavelength coming or how quickly the orange wavelength is depleted. Right, so that's how we're going to use the UV. The UV will monitor one specific wavelength and it will see how quickly something changes. And that's how we're going to use the or examine the isomerization kinetics. That's what I say here. They have different colors, different absorbance at specific wavelengths. So at a wavelength, we're going to be able to monitor whether or not one is being used up quicker or how quickly one is being used up versus the other one. That's all the mathematics as written in the practical guide, right? Which we'll also get to, don't worry. Remember, I'm a physical chemist, so we'll get to that. Right, so what's our procedure for determining the rate of isomerization? First, we're going to scan the absorbance versus the wavelength of each complex. So that graph that you see in your practical guide, you know, both of them have already been plotted for you, so you can actually go look at that. Then we're going to determine the maximum wavelength or the maximum absorbance point, so the wavelength at which there's a maximum absorbance for both of them. should be quite easy. There's actually 2 points, but one of them is quite explicitly the best option. Then we're going to isomerize the trans complex fully to the cis complex. We see that takes about 2 hours. I say it takes about 2 hours. Of course, I've done the experiment before, so it takes about 2 hours. Then we're going to prepare a fresh isomerization reaction. And we're going to compare the changes in this lambda. So in other words, monitor this lambda for an hour and see what is the change in the absorbance measurement over that hour. So how does that intensity decrease while this isomerization takes place over the course of that hour? The one should increase, the other one should decrease, right? Because the one is isomerizing to the other. Okay, and that's what that isomerization part is trying to test. So we're going to use UV-vis to measure. So it's essentially saying, because we're asking the UV instrument, how much green is there, how much orange is there. And the orange is being depleted, the green is increasing. That's what the UV instrument is going to tell us. Okay, in layman's speak is what it's telling us. All right. Of course, the numbers then make a lot more sense. Okay, so what I want to do now is I want to look at the most important parts of the mathematics of the derivation of Guggenheim's method. And we start with just what you should know is a first order rate law, or integrated rate law for the decomposition of a species A to B. So like the trans isomer essentially decomposes to the cis isomer. You can see that as a reaction and it has some rate constant K. A first order rate law is this: concentration at some time t is equal to the initial concentration of the species A times the exponent to the minus kt. Right. And from the Beer-Lambert law, we can also write this in terms of the absorption. I make use of absorption for the symbol D. I don't use A because there's like 14 A's going around here, so we don't use A. And we use D, so we just make a simple substitution. You can substitute in, remember C is technically concentration, just do the mathematics. If you don't want to do it, just take it as is. We can write it in terms of absorption. All right. And the Preprac guy goes on, and I say Preprac guy, I say myself, goes on. I take the ln of both sides, and then from the logarithmic laws, we get to here. Ln of a product is just the sum of the two things. Ln of E is 1. Take that forward, becomes that, right? Why is this significant? Because this becomes a constant, because your initial absorptivity is a constant, and it means then that if we take a plot of ln of absorption of a species versus time, the slope of that plot is going to give us the rate constant. And that's exactly what you did in 282. Remember, you had a plot and you had, for example, the concentration on the one axis and you had time on the other axis and you had a straight line, and then from the slope you determine the rate constant, right? Exactly, that's exactly what we have here. It's exactly the same thing, but now we have a problem. What is our problem? The problem is that we have both A and B contributing to this dt, to this absorptivity at this wavelength that we are monitoring. Remember, if you look at that slope, we're just looking at the lambda max, and at lambda max we have both of them still absorbing. It's not that we have a completely discriminatory graph, that we have one absorbing at one wavelength and the other absorbing at a different wavelength. We have both of them absorbing at the same wavelength still. We just have a good difference between the two. One is strongly absorbing and the other is not as strongly absorbing, but we still have a contribution from both of them in this, or at that wavelength. So that's our problem. So this is for, typically if you have one species, this is a great method. Now we have two species absorbing at the same wavelength. So what do we do now? How do we look at how do we determine the rate constant if we have two species absorbing at the same wavelength and we still want to apply this method? Okay, so that's what the Preprac guide develops from there. So in principle, what we actually have is an equation as such. We have the molar absorptivities of our two constants of our A and B species also contributing to the absorption. And of course, that means we require information about the initial concentrations and of those two things. And then that makes it difficult because we're not sure really what we're measuring at any time. But we can use a simple trick, which is Guggenheim's method, to use the temporal displacement of the system to change the playing field, if I put it like that. So if we look at where the time dependencies are, time is always somewhere, time is always there at the places where we don't have the information. And essentially, if we measure the system, we look at the system at two different times and take the difference between the system there, we can start looking at individualized constant. We can keep certain parameters constant and we can change other parameters. And that's what the method is trying to do. So that's what now we're looking at t plus h. That's what that's going to do. So what we have at time t is we have that equation. Then if we look at some time t plus some time in the future, so let's say t plus 2 hours, then we have a different equation. And if we look at their difference, we get an equation which resembles the one, remember, that we had there at the way beginning for one species. We have the ln of something equals to minus kt plus some constant. And even if that is all you take from this slide, is that we get eventually to this point, that we can, if we have this, we take the difference between, we have an initial measurement, and we have a 2 hours from now measurement, we take the difference between the two of them, and then we get to, by some mathematics, foolery, magic, whatever we want to call it, we get to a point where we can measure the slope of that graph, then that's also fine. We're not here to test your mathematical abilities, we've already done that. So that's essentially what Guggenheim's method tries to do, is it goes through a temporal displacement, and that allows us to keep the things constant because these things remains constant even though we change the times. So we've changed the time and the constants will always remain, those things will remain constant, the molar absorptivity and the initial concentrations. And then by varying the time, we can actually reduce those into a constant term. That's a very nice trick, or not trick, just clever way of approaching the problem. Okay, so you see the similarities between that and the previous equation that we had at the way beginning. So that's what we do. Okay, so how does that translate into the chemistry? That's what I'm going to discuss next, so like the data, like the physical raw data. So in a chemical sense, how do we do this? So how do we get T and T plus H and measure the absorbance and get the difference, and what does that mean? Okay, so it means we have two test tubes. The first is we have a fresh reaction. So it means we have something that we've just made immediately, and we start measuring the absorbance immediately of that. We also have an old reaction, something that 2 hours ago, because we know it takes about 2 hours for the system to fully isomerize from the trans to the cis, and that has already taken place, which we also measure the absorbance. And then we measure the absorbance starting at the same point. So you make this, so 2 hours, so let's say at 10 o'clock, you make this. You go have T. And at 12 o'clock, you make this. Then you put these two you put these two samples into the UV-vis spectrometer. And then only do you start taking your UV-vis measurements. Then only do you start measuring the D, the absorbance. So you then have the fresh measurement. So the fresh measurement is, of course, going to constantly change because that is now only starting to isomerize. The old reaction should remain constant because that is already isomerized, right? And then you take that difference. So in Excel, what you will have is every 60 seconds or every minute, you have a measurement of your fresh reaction. So that is isomerizing, that has an absorbance measurement, 2 up until 60 minutes. The old reaction remains sort of the same for that time because it is already isomerized for 2 hours. And then you say total, so in other words, old minus fresh, because that's T plus H, so old is T plus H, and then the total, the new one is fresh, so that one minus that one gives us this column, right? So that is what we do in Excel. And that is, remember, in the big equations, that is what we were looking for. That is chemically what that mathematics translates to. So this column, you then take the ln of that column equals to minus kt plus whatever. So what you do is you plot the ln of this. So you can have an extra column, the ln of that, versus the time. So ln against time. And like I say, so ln of d prime versus time. You take that slope, that gives you minus kt. So y equals mx plus b. This thing is just your b. You don't have to calculate individual terms or anything here. That's just a constant. So you just say that is b. X is your time. You have your time measurements here. You have your d prime, which is your difference in between the old minus the fresh. And then it gives you your straight line, from which you can measure minus k. Right. So actually very easy. Mathematics seems very daunting at the beginning, but it's actually quite straightforward what you need to do. Right. So I hope that makes a lot of sense. You make something 2 hours, you wait for it, you don't make any measurements on it, then you make a new batch, and then you measure them simultaneously from 1 minute. So in other words, it's essentially 2 hours and 0 minutes, and then from there on, the first measurement for old one is 2 hours and 1 minute, and this one is at 1 minute. And then from there on, you have the measurements. So this one's final measurement is at 3 hours, and this one's final measurement is at 60 minutes. Difference between them, plot the ln of the ln against time of these two. You can plot the time, of course, for the difference, for the ln of the difference as 1 to 60 minutes. Don't go and add 2 hours for this one or whatever. Don't do anything weird like that. Time here is just an arbitrary unit. It's just 1, 2, 3, whether or not it would be 3 hours, whatever. It's just units of one. The differences remain 60 seconds. So that's why it works out. Trust the system. So that ln of it against that time will work out. Okay, so let's talk about what the data should actually give you. Okay, so the first important point is from now on, just disregard the colors. Colors just mean they're just different colors. And I want to look at the data. So if you start plotting the data, there's 3 data or different data sets I give you on ClickUp. You need to judge which ones you would like to use. So a good place to start is to see what do we expect. So if we just make a plot of our absorbance of the 2 samples versus time, we should expect our fresh reaction, our fresh reactions absorbance to increase towards what the old reaction is already at, sort of by the time we start measuring. Because remember, the old reaction is already isomerized to a certain point, and our fresh reaction is going to isomerize to that point. So we should see a convergence between these 2 data sets from the beginning. So remember I said it should remain constant. That is very nearly constant. It's going to increase slightly over the course after the 2 hours still, but that's much more constant than what this is, for example. So the fresh, over time, the fresh reaction should reach the same absorbance as the old reaction. So that's what you're looking for. So remember, if you plot just the absorbances of the 2 data sets or the 2 reactions of a specific data set versus time, then you should see something like this. In a similar manner, if you plot the difference, in other words, if you take old minus fresh and not the ln yet, just the difference, and you plot that versus time, you should see an exponential decay. So in other words, the difference between those 2 things should become smaller exponentially as we would expect for a first order decay reaction. So in other words, it still makes a lot of sense. And that is ideally what you should see. So these are the things that you're looking for in the data sets. But also, what shouldn't you see? If you, for example, had different concentrations of your trans isomer at the beginning. So in other words, you need to have for the two, your old and your fresh reactions, you need to have the same concentration starting, even though the one starts 2 hours before the other, you start with the same concentration. If you had a higher concentration for your fresh reaction than your old reaction, your absorbance is of course going to be higher. And you're going to see that in your difference between the two absorbances. You also see that there. You see your difference increases essentially over time, and it gives you the inverse of what you really want. That means that you end up with data that's really not usable. In a similar vein, if you, for example, let's say, for example, you made your reaction at 2 hours and the other one you made at 1 hour after the other one, and you only start measuring an hour after you've made the fresh reaction, then you would see already the plateau has already begun, and then you would see there's a problem in your difference. So in other words, your fresh reaction is not really fresh, it's already an hour old or something like that. It would also have some problems. So these are the things that you can use to judge whether or not which one of those three data sets would be the best to use. All right, so I've now given you an idea of what is perfect data and what is not perfect data, essentially. Right. Okay. So that's all I wanted to say on the isomerization. Let's move on to the final part, which is the ML3 complex. So your ML3 complex, here it is. So now we've substituted the two aqua ligands for another oxalato ligand, right? So this is how our full ML3 complex looks. So chromium oxo 3. Remember the charge. Chromium is in the 3+ state. There's 6-. In other words, 3-. There must be a potassium 3+ somewhere, or 3 potassium pluses. Anyway, there you can see it nicely. And remember, there's no cis and trans here because they're all the same. They're all the same, right? So there's A6. Right. So now my question is, what type of isomers are possible? I just said there's no cis and trans possible, but what isomers are possible? There are isomers possible. So are there structural isomers possible, geometrical, or optical? So remember, cis and trans are geometrical isomers. So which one of the other two type of isomers would be possible in this case? And in the theory course, you should cover specific type of isomer, or otherwise, I mean, the literature is always your friend. That's all I want to say about that. This is the ML3 complex. So this is technically synthesis 2.1.1. I did this at the end, but you need to go and read up a bit on the isomers, or the different kind of isomers that is possible for octahedral complexes. What is an optical isomer? How do you name them? Why do they exist, etc. And then just finally to recap. So firstly, you will synthesize the ML3 complex, which is the tris oxalato chromium complex. That's experiment 2.1.1. Then you synthesize the cis and the trans complexes. You test the purity, remember the polarity, that's how you look at it qualitatively. You determine the lambda maximum for the isomerization kinetics, and then we collect the isomerization kinetics. The data is provided for you on ClickUp. You need to discern which data set is the best data set for you, and essentially from there on, that's what it is. How it works is the synthesis. You cover the synthesis in week 1, and then you test the purity and do the UV vis in the second week. The groups are divided for you on ClickUp or per laboratory, so you know when you need to go where according to your group for the UV vis, because we can only accommodate so many people at a time in the UV vis lab. And yeah, that is what it is. I hope you prepare well, and good luck.